You want to know 0.10 is what percent of 3 liters. So what you do is you turn this into an equation. 0.10 is what percent x times 3, and then you divide by 3. 0.10 divided by 3 is x. I think you said you were multiplying.
So, was this right?
0.33. Yeah, I think so. Yeah.
Okay.
Yeah, but this should be times right there.
Times?
That should be times.
Okay, that's where I'm getting it wrong.
Yeah. Okay, let's get started. Y'all ready? Y'all ready? Pokemon, we can, if I say Pokemon, everyone just starts blowing up. Everyone goes crazy. What's that? I don't know, is it Pokemon? Pokemon what? Oh, sorry. Sorry about that. I don't want to offend anybody. Pokemon. I have a question for you up here. It's math related, but it's definitely not something that you'll be tested on, but it's something to consider. I'm curious what your responses are going to be to this. What's 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever? Yes. The answer is yes? What do you think?
Wait, I forgot the
You did what? Return it? 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever. What do y'all think? Infinity? Okay.
0.
0?
-1.
-1?
+1.
23?
85.
I mean, really, you look at that, maybe you don't care, and that's fine. But I'm just curious, like, what you might think that is.
0.
0?
That's my final.
That's your final? It never stops.
Is there an answer?
That's a great answer. Is there an answer?
Plus minus 1.
So it could be either plus or minus 1? Okay, so look, how about this? Let me try and convince you of a possible solution to this. Let's just call this S. All right, let's just call that S. S for sum. Okay? That's a sum, isn't it? Okay, I'm going to write S again. I'm going to write it below. I'm going to write it this way, though. Well, it's the same thing, right? Because if you add 0 to something, it's the same, right? Now what I'm going to do is I'm going to add these two equations together. So in other words, I'm going to write S, and I'm going to double it. I'm going to add it to itself. S plus S. If I take S and I add S to it, how many S's will I have? 2 S's. So do you agree that 2 S's should be this plus this, this plus this, this plus this, just adding them straight down? Okay, what's 1 plus 0? 1. What's -1 plus 1? 0. What's the next one? 0, 0, forever. And so what we get is that 2s equals 1. And if I ask you to solve that for s, you'd divide both sides by 2, and you would get 1/2.
But I feel like that's irrelevant to figure out another s, like 3s, right? So then it'd be 1/3.
Well, if you add another s in here, where are you going to put it? Where do you want it to be? Where?
So it'd be 0, 0, 1.
You want me to do 0, 0, 1?
Well, I'm just saying.
No, this it's a good proposition. If I did another s, how would you line it up to make all these zeros? I don't think you're going to be able to do that. Right? Because if I did 1, -1, 1, -1, then I'm gonna have things other than 0 that time. Yes?
Why did you put the 0 at the start?
Because I knew it would work.
Well, yeah, I know, but like, what specifically is the 0?
Because I'm trying to make you think about something that doesn't feel natural. I'm trying to give you something that you don't like up here. All right? Here's another one. 1 + 2 + 3 + 4 forever. What do you think about that one?
I feel like I would just put a greater.
What's that?
That's out in the hall.
I don't know. Is it?
It is over there. It's going in.
Is it?
There is something like that right there. Yep.
Right here?
I just don't even pay attention. Right around the corner.
Really? I'll look. I'll go look. I'll go look. Huh, that's interesting. I didn't even know that was there. Y'all want to know what this one is? -1/12. What? Does that make any sense? No. That makes no sense, right? You have a bunch of positive numbers, you're adding them up, they're getting bigger and bigger, you do it forever, and it gives you a negative fraction. If you go right now, which I know none of you are doing, but if you were to open up a textbook on quantum mechanics or quantum physics.
I read that yesterday.
Got it? Okay. This is usually in the first chapter, is that you have to assume that this is true. And all of the quantum theories are based upon this summation being true. And what's interesting is that in the real world, in the physical world, when we test things and we take readings, we actually come up, this sum appears. And when we replace that sum with -1/12, all of what we see and observe matches with the mathematics. It works in the real world. It's very strange. We can't really explain it too well, but there's a proof. I could show it to you. I'm not going to. Of kind of like how I did with that S thing, and just add another S, and I could do that and show you this is true, but it would take about 10 minutes. So, okay. Hopefully that shifted your brains off of Pokemon for a minute. Let's continue factoring. Pokemon. All right. So what if we have two terms? If two terms, we use a special formula. I could tell as soon as I said quantum mechanics, everyone was like, who cares? But I think it's somewhat interesting that a lot of the modern day physics is based upon some pretty absurd ideas that don't really make a lot of sense. But it seems to work, so. Do y'all want to do this, or should I keep talking about quantum physics? Physics. Wow. If you have two terms, the only thing that we are going to look at in this class is if you have what's called a difference of squares. So in order to factor two terms, a two-term expression, we must have a difference of squares. That means it must be something squared minus something else squared. If that happens, we can do it. So here are some specific examples of difference of squares. X squared minus 49. Another one, x squared minus 81. X squared minus 25. These are all difference of squares. Right? You have two terms in each of these. This is a number squared. This is a number squared also. It's not as obvious because it's not written as squared, but it's 7 squared, right? This one is 9 squared, and this one is 5 squared. I'm pretty proud to say my 7-year-old daughter knows all her perfect squares up through 15. It's pretty good, right? I don't even ask her. She just wanted to learn it. I was like, we started out with like 1 times 1 and 2 times 2 and 3 times 3. And every night when we go to bed, she's like, okay, let's do the squares. And I'll quiz her. She'll be like, don't give them to me in order. And I'll give her to them like, 7 times 7. And we're every few nights we add another perfect square. Yeah. So, but now I'm having to like get my calculator out and like double check. I'm like, okay. Of course, because I really only know like up to like 12, and after that I don't care, That's all you really need most of the time, up through 12. You're good? Okay. All right, so these are perfect squares. Sorry. And because of that, what's the formula for it? Does anyone remember what it is? I didn't put it down up here. Oops. It's always going to break down to be 2 factors. It's going to be the x plus the x minus the a. And it doesn't matter which way you write those. X plus a, x minus a. So for us, in this problem, we would write that as what? X plus 7, x minus 7. Done. It's factored. Next one. X plus 9, x minus 9. Next one. X plus 5, x minus 5. Got the pattern? If this is a plus sign, there is no way to factor it. It's not factorable. Got it? There are also 2 more formulas that we're not going to cover in this class. There's a difference of cubes. There's a formula for it. And there's another one with the plus sign. You can actually, there is a formula for this one also. So we won't focus on those. Just be aware that they do exist.
So it's only with when it's
Yeah, when you have the cubes, there's a formula for both. When it's squared, there's only a formula for subtraction. So let's do a.
Did you say that last part was if it's positive, you can't
If it's a plus, you can't do it. So if someone wrote down, hey, break this down, factor that, you'd actually say it's prime, not factorable. All right, so let me give you a problem. X cubed plus 3x squared minus 9x minus 27. I would like for us to factor this. So what are you thinking? Greatest common, good. Who said that? Good. Greatest common factors first, right? Don't forget that. GCF, do we have one? No, right? Don't have a number or a letter in all of them. So move on. Terms? 4 terms. Grouping. What comes out of the first one? X squared. What's here? X plus 3. Good. Next one. Do y'all like that matching thing where we just write it? Okay, let's just do that. And now you have to turn x into negative 9x. Your only option for that is negative 9. And just double check, negative 9 times 3 is negative 27. So it works. What is the next thing that you write? You had 2 options on how to write this, don't you? X plus 3 minus 9. And you box that up and you turn that in and you don't get full credit. Why? Ah, that's a difference of squares. See, I hid it in here. See the difference of squares there? X squared minus 9. That breaks down further. This one doesn't, right? Because it's not even a square, so you don't have to worry about it. But this other one turns into 2 things. And what does it turn into? X plus 3 times x minus 3. Huh. Now it's factored completely. And you can even go one step further. You could put x plus 3 squared times x minus 3. That would be completely factored in the cleanest notation. Do you see these are the same? I'm not multiplying them together and doing FOIL, right? I'm just saying, hey, look, anything times itself is that squared. So I'm just rewriting that notation. How about this? 81 minus x squared. Can you factor that? Now, this is the same as 9 squared minus x squared, right? So do you agree that that's still two things squared, subtraction between them? So it should look a lot like what we just did. What's different though? It's instead of like this, where we did x plus 3, x minus 3, they're switched. So it should be 3 plus x, 3 minus x. Notice how they switched roles. It does matter, yes. Well, maybe. How are you going to write it? Were you going to write it like this? Yeah, that wouldn't work. Because if you wrote it like this, you're saying you would write it like this, right?
No, I was going to do x plus 9x.
Nope, not 9, because then it would be 81. Oh, shoot, I'm sorry. I'm sorry. That's my fault. It's my fault. Sorry, my fault. How are you going to write it? This way? That's still not going to work, though. This doesn't work, sorry. But mine was way off, okay? This, when you multiply this, watch what happens. 9 times 9, 81. 9 times negative x, negative 9x. X times 9, positive 9x, so those are gone. 81 minus 9x plus 9x minus x squared. That's what you would get if you multiplied those out. These two would cancel, you get 81 minus x squared. If you do it this way, then you get x squared minus 81. And that's not the same, right? X squared minus 81 is not the same as 81 minus x squared. So if the order changes, all you do is you just switch them in here too. All right. That's it for the factoring. And now we are going to do solving quadratic equations. Pardon?
I said, I thought we were sticking with that.
I don't think so, no. No. Solving. Let me see yours. Is that the one you bought in the bookstore? Let me see yours. I thought I checked these before. Go back on here. We're doing this right here. Yeah. Yep. We are going to solve quadratics more, okay, later, but now what we're doing is solving quadratic equations with factoring. So what's the purpose of this whole thing of factoring? Like, why do we do it? What's it useful for? And it's for solving quadratic equations. Yes. We're still on, let me look at yours. Page 30, page 55, part C. This right here.
Yeah.
That's what we're doing. Yep, and one unknown. Yep. All right, so let's talk briefly about what a quadratic equation looks like. Any quadratic equation looks like this. I like when possible to at least give some meaning to why we would want to do something, especially in a class like this when everyone's like, what are we doing here? So let me try and motivate the idea a little bit. Does anybody know what a quadratic function looks like if you graph it? What does it look like? What do they call those things? Parabola. Y'all heard that before? Parabola? If you were to sit there and graph this, in other words, if I were to write, y equals this, we saw that like if it was y equals mx plus b, it's a line, right? But if it's y equals that quadratic thing, it looks like a parabola. And parabolas look like this. They look like U's. And we usually say they open up or down. We're going to talk more about this later, all right? I just want to kind of introduce why we're doing this. And these are very, very useful to us, believe it or not, all right? Now I'm going to give you a demonstration of why. You want to help me out, Sean? You don't have to get on camera. You just have to go stand over there. Sean's going to help me out. All right, Sean. So I'm going to throw these to you, and you're going to catch them. All right? I'm going to toss them. All right. So just watch the markers go through the air. All right? All right. Good. Good job. Okay, throw them back. Oh, okay, try and lob them up a little bit. There we go. Okay. Good. So, good. Perfect. All right, so the path of those through the air, right, is curved. And it's not just any curve. It is a parabola, guaranteed. There's no question about it. It has to be a parabola. So it could look like this. If you lob it really high, it could look like this. It just depends. If you throw it really, really high, it's going to look, something like that. And so, as humans, we've over time realized that the things that we observe physically can be modeled mathematically, and a quadratic function is the way you model things flying through the air. Now, why is that useful? Well, I'll tell you probably the most useful part of it, or what motivated it the most, and that was back in the day when you had things like a castle. This is a castle, okay? That's a castle, and you want to attack the castle. You want to pillage. You want to take all the food, and kill the people that don't agree with the way you believe and all that stuff. Right? We love that shit, don't we? Don't we like that, humans? We do. Okay, so if you want to effectively tackle that, you can just start lobbing stuff at it. You can start throwing, cannonballs and whatever. But at some point you realize, you know what, I can be a little better than just hope I hit. You can actually hit where you want to hit. If you understand the mathematics behind the projectile, what its motion is doing, right? Then you can accurately put it where you want it. So that motivation of wanting to, unfortunately, wage war upon each other has motivated mathematics in ways that it would have never advanced, right? Think about the atomic bomb. What was the motivation of that? We better get it before the Germans get it, right? Or else we're screwed. So it was that need, right? So understanding a quadratic function helped us do that. And then now it's everywhere, right? You're on your phone, right? How is your phone communicating? It's sending signals through the air. And you've got these satellites that are catching them. All satellite dishes have a little thing on the inside, right? They're all curved. If you were to cut this open, it would be a parabola. And the property of a parabola is that if you've got things going into it, it bounces off, and everything bounces. Just the way it's curved, it's perfect. All the things that go in bounce, and they all go to a single point. That's called the focus. Now, if you take a basketball and you cut it in half, it won't work. It's not shaped properly. It has to be parabolic. It has to be quadratic. So we realize that, we discovered this, and we use it, with our communications to this day to wage war upon each other. It's wonderful. Okay, so with that in mind, knowing that parabolas are useful to us, we are going to eventually want to know what the x-intercepts are. And x-intercepts of a function, like we did with the lines, we always said, okay, to find the x-intercept, you set y equal to 0. So if we were to treat this like a function, y equals that, and I ask you for the x-intercepts, you would replace y with 0, yeah? And when we do that, we have a quadratic equation, and we're going to try and factor it and solve it. Okay. So let's do this. Before I can do it, though, I have to make sure everyone is on board with this. It's called the zero factor property. This is a major property. We don't want to take it for granted. All right, if I tell you right now, A times B equals 0, what can you tell me about A and what can you tell me about B? Or can you tell me anything about them? What's that? One of them has to be 0. One of them has to be 0. So if A times B equals 0, then A equals 0 or B equals 0. One of the two have to be 0. There's no other way to do it. Can anybody try and come up with a way to make two numbers multiply to be 0 without one of them being 0? Negative 1 and 1? But it's multiplication. So that's going to give you negative 1, right? It's a good try. It would work with addition, right? But not with multiplication. So you can sit there and you can try all day long. You're not going to ever come up with it. All right? So two numbers multiply to be 0 means one of them has to be 0. What if I added a third number in here, times C? One of the three, right? A, B, or C have to be 0. If I have four things, one of the four things has to be 0, right? The important part of this is they call it the zero factor property for a reason. This is the key to it all. 0. Let me show you something different. What if I tell you that two numbers have to multiply to be 2? What can you tell me about A and B? Does one of them have to be 2? No. Doesn't have to be. Could be. Right? I could do this. 2 times 1, and that would give me 2. Okay, so look, one of them was 2. But do one of these have to be 2? No. Give me an example of two numbers that wouldn't be 2 that would give me that. 4 times 1/4 is 2, and neither, right? That's 0.1. That's 0.25. I'm having lots of these today. 8 1/4.
Or 4 times 1/2.
Or 4 times 1/2, like you said. Sorry. Right? So yeah, 4 times 1/2 is another example. So look, you can sit here all day long and you can come up with examples of two numbers that multiply to be 2 where neither one of them is required to be 2. All right? So this only works if this is a 0. And that's why it's going to be so important for us when we're looking at quadratic equations that we always make sure they are set equal to 0 before we begin. So keep that in mind. And we get to the first example. 9x squared minus 16 equals 0. So is it a quadratic that is set equal to 0? Yes? This is a quadratic, isn't it? X squared, that makes it quadratic. It's set equal to 0, so we're in business. We just need to see if we can break down the left side into to be something times something. Right now it's something minus something. But that's what factoring is all about, right? Does anyone know how we would attack this? GCF, do you have GCF on the left side? No? How many terms? 2, okay, special formula? Difference of squares, that's all we've got. Is that a difference of squares? Is it something squared minus something squared? Isn't this 3x squared minus 4 squared? I'm writing the 4 in parentheses even though I don't need to. Yet the thing you have to be careful for is this 9. When you square 3x, You square the 3 and you square the x, which would give you 9 and then x squared. Minus 16, which is 4 squared. So using that formula that we had, what would we have in these two parentheses? What would go here? What would go here? 3x minus 4, that's fine, and then 3x plus 4. And you could do it the other way around. You go 3x plus 4 and 3x minus 4. All right, Joshua. You look like you need some motivation. What are you going to do with that, Joshua?
That would fit what we needed. One of them would have to be equal to x, or 0.
That's right. You have two things that are being multiplied together here, right? A is this big chunk and B is this big chunk. They're being multiplied together to be 0. That means one of them has to be 0. So let's investigate that. At this point, either 3x minus 4 equals 0, or what? 3x plus 4 must equal 0. Do you see, this is where I'm using the zero factor property. And since Josh is on a roll here, Josh, well, you wrote Joshua, so I'll go with Joshua. Joshua, what types of equations are those? Linear equations. And how do we solve linear equations? We isolate the x, right? Isolate the x. So now we're back to stuff we've done before, right? So here I'd move the negative 4 to the other side, which would make it positive, then divide by 3. X is 4/3. Over here, move this over, become negative, so negative 4/3. So you might have to do a little bit of work, but you should get to those two results. So what we're saying is for this equation to be true, right? For this to be true, either x has to be 4/3 or x has to be negative 4/3. If you replace it with that, then it should be true. All right, let's do another one. How about 4x squared equals 11x plus 6? So now we want to start to really focus on, thinking what type of equation am I looking at? So you look at this, right? It's an equation because there's an equal sign. It's x squared, not just x, so this is quadratic, right? What is the method so far that we've developed to solve a quadratic equation? Set it equal to 0. So that means you got to get everything to one side. And it's up to you, left side or right side, it's your call. I'm just going to move everything to the left. So when I say move everything left, what does that mean? Switch the signs, right? Subtract all this, put it over there, it becomes negatives. Hold on. Did I write that down right? Sorry, let's make this a minus 6. Minus 6 here. Everyone got that? Change that to a negative. So when I rewrite this, it's 4x squared minus 11x plus 6 equals 0. And keep in mind that when I wrote this down on the left side, when I rewrote it, I put it in what we call descending order, which meant I went from the highest power of x down. Okay, so x squared, x, and then no x's. That's called descending order. Now what? Greatest common factor. So we're going to start trying to factor this out. We try GCF, no go. Okay, how many terms? 3. So we try AC by grouping, unless you can do it mentally. AC by grouping is going to be, what number up here? 24, number down here, negative 11. What if you can't come up with these numbers? What if you just cannot come up with these numbers on your homework and you're stuck? I want you to write prime. That would mean it doesn't factor, and it could happen on your homework. But make sure you've checked all your numbers, because it could be that you just can't find them. That you didn't check thoroughly enough. But if it does not work, just put prime as the answer. Doesn't factor. Does it work in this case?
Yes.
Yes. What are they? -8 and -3 again. Negative and negative. That will work. Pardon? Good? Okay, so what I'm going to do now is I'm going to rewrite this trinomial over here. And I'm going to rewrite the -11. I'm going to do my 4 terms. I'm going to do my grouping. And then, so I'm kind of building off of what we've already done today, right? What did I say would happen if you switched the order? You put the -3 and then here and then -8 here and you switched them here. It should still work, okay? You should still be able to get to it. So this, sign-in sheet's coming around. Remember, you're allowed 2 absences. You're allowed 2. I think what was the highest grade on the test? Was it 98.6 or something like that? If the people who got like the highest 3 grades in the class had missed more than 2 classes, I might talk to them about, okay, that's okay. But if you're missing 2 or more classes and you're in the 70s on your test, then that's going to be a problem. I'm talking while y'all are finishing this up. Who has this? You want to share?
I got 4x minus 3. And x minus 2.
Agree? Agree? All right. Looks good. You could always check, right? You could just check. I like to do quick little checks. This is 4x squared, so that's good. This is going to be -8x and -3x and -11x, good, and -3 and -2 is 6, so yeah, it works.
Is that going to be the same if you subtracted the
If you subtracted the what?
4x squared? For the beginning, like instead of moving your
If you would have moved it to the other side?
yeah, the next one.
It would work. It'd be a little tricky, but it would. You get the same answer. You would not get the same factors. These factors would look different. The question that's being asked is, what would happen if you would have taken this to the other side? Right? That's your question?
Yeah.
Your AC method would have looked different too. You would have had, let me see. Well, no, 24, and you would have had positive 11. So things would change, and numbers. It would be a little tricky, but at the end of it all, we should have the same answers. So what do I do at this point? Set each of them equal to 0. So 4x minus 3 equals 0. And then x minus 2 is 0. And then solving each of these, 3/4 and 2. So it's either 3/4 or 2. One more. Mm-hmm. 30x cubed equals 2x squared plus 4x. Uh-oh. So you should probably be looking at that saying, hey, that is not a what? Quadratic equation, because it's not squared. It's not squared, right? The highest thing you have there is cubed. That's bigger than squared. Yes, so the question is, what do you do with this? And our technique is going to be exactly the same. We're going to move everything to one side and let it equal 0. All right, start with that. So how about I move everything to the left side? Subtract. Put it in descending order, and you should have that. Are you all comfortable with that step, just moving everything? All right. Now we said, the zero factor property said a times b was 0, but I also told you that a times b times c is 0, and I said a times b times c times d. The more I add, it doesn't matter how many things multiply to be 0, you would just keep setting each of them equal to 0, right? If it's 2 things or 3 things or 4 things. So when we look at this trinomial, we look at the GCF first to try and factor, right? And I believe we have a GCF here. What is it? 2x. We can actually pull 2x out, can't we? So 2x comes out. How many terms will we have in there? 3 terms. What are they? 15x squared minus x minus 2. That good? Everybody sign in? What am I missing here? Equals 0. Let's not forget we have an equation. And now, this is a trinomial in here, right? AC method on that trinomial. You all understand what I'm doing? On this trinomial. The 2x I'm going to ignore, but I'm not going to forget it's there. What goes in that little thing here? Negative 30. We got that from doing the 15 times the negative 2, bless you. See, I'm ignoring this, bless you. I'm ignoring this completely, and I'm working with just that. 15 times negative 2, negative 30. Number in the middle? Negative 1. Okay, so now you get to play your game, try and come up with 2 numbers that multiply to be negative 30 and add up to be negative 1. You sit there, you punch away in your calculator maybe, and eventually you figure out it's negative 6 and positive 5, right? And that allows you to now break this thing down. Got to keep the 2x out there. So this, we're going to have lots of parentheses, and if you wanted to use the brackets, you could. I'll do this one with brackets just so you can see it. 2x is on the outside. Then I'm going to rewrite the 15x squared as 15x squared. Instead of minus 1x, I'm going to put what? Minus 6x plus 5x. It's using these 2 numbers. And then minus 2, and then I'll close my bracket off, equals 0. And we did all that for what? Why did we do that? I forgot why we did that. So we can group it. And then we group the inside. What do you have as far as a GCF here? Just x? 3x, okay. 3x, you can pull more out. So 3x. 5x minus 2 is what you would have here. So checking it, yep, you get that back. How about over here? Ooh, this one's tricky. We haven't seen one like this. But this is a very important problem. That's right. So we know that we need this over here, right? But you have to have something out here. You can't just leave it empty. So we put plus 1. See, because it matched up. So 1 times this is this, 1 times this is this, and we're in business. Close the bracket, equals 0. Does anyone have any questions over that step? That's pretty important. Yes?
Why do we need the 1? I mean, it's obviously going to just be 1 if there's nothing there.
Yes, well,
We'll use it later.
are we going to use that? We're going to say it's going to be this times what? 3x plus 1, right? So if you don't have that there, you might forget that. You might just write, like, I don't know what you'd write. I've seen everything, okay? I've seen people forget it completely. So you see what I'm saying? Like, you're going to do 3x and then
Well, it'd just be plus the parentheses.
what? Be what?
It'd just be plus.
3x.
Need a plus sign.
You mean you need a plus here? You're saying just put a plus there.
Yeah.
Okay, so what are you going to put here?
You would need the 5x minus 2.
Okay.
Yeah.
And then what goes here? See, that's why it's so important to put plus 1 out here, because what goes here is 3x plus 1. It's this, and then it's this and this in a parenthesis.
That makes sense.
Okay. I'm trying to sell you on it.
Yeah, I know. I was just trying to understand the logic on why you need
Yes.
Yeah.
It technically doesn't have, the plus sign has to be there, the 1 doesn't. But it's good to put it. All right, so we rewrote this as this, and then remember we had the 2x out here. I got rid of the brackets because it's all multiplication now. And so, there we go. Now set each of those equal to 0, right? There's 3 things being multiplied. So I'm going to have 3 equations here. Here they are. 2x must equal 0. 5x minus 2 must equal 0. And 3x plus 1 must equal 0. Those are my 3 equations. To solve the first one, I just divide both sides by 2. 0 divided by 2 is 0. Here we move the 2 over, divide by 5, we get 2/5. And then here we move the 1 over and divide by 3, we get negative 1/3. So in order to make that equation true, the very beginning, you would have to let x be one of those 3 numbers. All right. Well, it's been a long week, 4 days in a row with an exam. It's over. Please do the homework. I want to be specific, so because these things aren't matching up, I want to tell you exactly what the pages are on, or what pages to do. If you're working off the printed version, off the one I provided online on Canvas, which is the one that I have, it's page 59, and you should do 1 through 17 in part, oh wait, why doesn't it say part A? 1 through 17, and then 1 through 19. So both sections.
You only have 2 sections?
Pardon?
You only have 2 sections?
Yes.
You have 30, or 18.
Hold on a second. Hold on. And then if you're, can I borrow yours? If you're on, this is the printed one. This is the bookstore one. Page 57. One through 124 or 23. Is that fair? No, I'm kidding. Y'all are screwed. Haha. Okay. Page 57. Just all of them on page. Seriously, all of them. It's 17. It's 17 problems followed by 16 problems. So it's roughly the same, right? So just do everything on that page. Just, that's it, right? Because that's all we covered today, right? Make sure you do that by Monday, though. All right, so I can answer questions at the beginning of class. Let me turn my camera off. And then I'll answer questions.